Hi everybody, and welcome to a brief review of the C programming language. We're also going to do some reviews and competitions between beards, the classic Unix beard. So first of all, C, as we've been talking about, C has been developed by Dennis Ritchie and several other people at Bell Labs. These are the same people that worked on the Unix system in the first place. The development of these systems all happens hand in hand by, in many cases, the same group of people working in the same place. So we'll see a lot of carryover between function calls and names and conventions between the different systems. C is a successor to B, but at the time, B's inability to use the PDP-11's features, which is what Dennis Ritchie and Ken Thompson were working on, caused Dennis to go ahead and develop C. They needed some of the better horsepower that he was developing for it. And then they went ahead and rewrote Unix in 1972 fully in C, which had been in development at the same time. So let's take a look at beards right out of the gate here. Dennis Ritchie, the classic 70s beard, not hipster, not ironic, but actually plaid beard in the day. Richard Stallman is one of the great lions of the open source movement. His Free Software Foundation is legendary. The beard, on the other hand, is indistinguishable from the hair. So we're going to give the first round here to Dennis. As a high-level language, C is placed to provide a little less in the way of nasty pointers and jumps like you see in assembly, while still giving access to those. The original version had 32 reserved keywords and about 50 operators and syntax characters. The syntax, though, for C is what is most influential in all programming systems and all programming languages that we see nowadays. So C# and Java, they all take cues from various C syntaxes that are, of course, results from earlier development as well. Let's take a look at the most classic program here, Hello World. In the C case, the first C book, which was also written by Dennis Ritchie and Brian Kernighan, it contains the first usage of a Hello World program that was ever put in a book form. So while the concept had existed for a few years prior, it had existed only in a book form from the beginning of this book, one of the most famous programming books ever published. Often it's called KNR-C, just because of this book. Everybody, including my dad, who was involved in C and early Unix, has this book. So let's take a look. At the top here, we have an include statement, which is a preprocessor directive. So a preprocessor commands all start with the pound sign here, and what that's in reference to is the preprocessor runs before the actual compiler does, and that allows various include statements and even some rudimentary if statements to run to help change the code based on the environment you're in. In this case, we're loading up the standard I/O library. Let me turn on my little laser pointer here. There we go. The little standard IO.h library includes things like printf, which we use down here in our function. So looking at the function here, the int at the beginning of this function, the function of course is called main, the int refers to the type of data that will be returned by this function. And sure enough, the last statement of this function is return 0, meaning we return an integer, in this case 0. The first line of our function here is printf, which is a formatted print statement. We'll talk a lot more about printf in the slides and lectures to come. In this case, it merely outputs the term hello world, and then the \n is a new line character, and then it terminates itself. All functions have parentheses to open and close them, and a semicolon is required at the end of every line. Note that there is no semicolon at the end of the function. So that is our first hello world. For part 2 here, let's take a look at a slightly more complicated version of printf. In this case, the over 9,000 value is stuffed into what's called a floating point number here in our second line. By contrast to our first slide where we had an integer, this one loads a floating point number, and floating point numbers have an f after the decimal points and numbers here so that we can tell that they're floating points. Above that, though, we have our first pointer. This particular pointer is pointing to a character. So this type, this variable, is of type char, a character, and this one is a pointer, and we only know that because of the asterisk there. And our name of this variable is oblig. So the obligatory hello world here with our it's over 9,000 value, we can then print these all out. This statement, this printf here, the %s is then a field that will be filled in by variables that are to the right of the statement. So in the printf, first we have a quoted string, and in this case %s means that a string will be inserted at this point, followed by a new line. Our first argument here, oblig, is a string. A char star is a string in the C world, and again, more about strings coming up. That string then is stuffed into the printf statement here. For our next one, we have a it's over 9,000 statement here, and the / tick mark here is how we escape that character so that we don't have unescaped quotation marks inside strings. The %.2f lets us take the it's over value, which is a floating point, and have 2 digits worth of precision when it's printed out. That's what that formatted printing refers to. We can take a number like 9,000.0 and output it with 2 digits of precision. And down here is our output. So when we run this particular program, say it was HW2, it'll say hello world, and then we will see it's over 9,000, and we see the 2 numbers of precision at the end. Alright, and again return 0. Let's take a look at round 2 here. This is Brian Kernighan, the famous Brian Kernighan, helped in the C programming language and at Bell and a ton of other stuff. He has a nice large beard, but still shaped. Richard Stallman is just inexplicable. Let's look at some string shenanigans, of which there are many. In fact, we've got a lecture coming up that's just all about strings. This particular one here, we have 2 different libraries that we're going to load in. First of all, the same standard IO library, and then our string library, which will contain things like string length and string compare. When this thing runs, our program is called string shenanigans in this case, and when we run it, it asks for, or it lets us know that the length of an entered string is, say, 30, and then it lets us know that entered strings are not equal, so we can test and compare things that have been entered. So first of all, we're going to define a string, and this one the variable is called boring, and it contains the text boring. This particular string type is called a string literal. It is immutable and cannot be changed, and we'll talk a lot more about that later. But our next one here is another one called weird dad saying. As a kid, my dad told me this frequently, and I still don't know what it means, but he would say, hey, eat more beef and kick less cats. Again, no idea what it means, but he'd say it a lot. So we've got our 2 different strings here and a uninitialized integer called length. Then we take our length value and we'll go ahead and give it a value by using the string length function, which just gets the number of characters in this particular weird dad saying. Print it out that the length of entered string is, and here's a decimal value that comes from the length variable, and again length was set by our weird dad saying. Turns out it's equal to 30. Then we're going to do a comparison. And string comp, the string comparison function, only shows us equality when the 2 strings that are entered into the function are, the string comp function returns 0 when the 2 strings are exactly equivalent. You cannot use the equals operator on 2 strings directly. That compares the pointers behind the strings, which is not at all the same as the content of those strings. So in this case, this string compare function is being used to test boring and weird dad saying for equality. One of them is boring, and the other one is eat more beef, kick less cats. They're not equivalent, so therefore the if statement does not return true, and the else statement is printed out. Entered strings are not equal. In our next one here, we'll take a look at some arguments here in a strange function. This one is the string concatenate function. Same header preprocessor includes up here. In this case, our main function, its return type is listed as void, meaning it won't return anything. That's valid, no problem there. Note that there's no return statement here at the end. I'm going to define 2 arrays. And an array in C is defined by, first of all, the type of that array, the name of the array, and then in brackets, square brackets, the number of elements that make up that array. And C is famously 0 indexed in terms of how we refer to those. We'll take a look at that on the next few slides. We're also at the same time we will define another char array. Note that we don't have to put char here again, and we use a comma to split the 2, to show that there are 2. We'll printf out a informational phrase here, enter the first string, and then we're going to run a function called getS, which is going to get a string and set it into our character array, the character array A. We'll do the same thing again, enter the second string and put its results into array B. Then we're going to run the string concatenate function. What stringcat does is not only does it return a string that is the two strings that have been entered joined together, concatenated together, but it also puts the results into the A variable, overriding whatever you had in there, which is fairly strange design. In more modern instances of these kind of functions, we're more used to having the return value be the only thing that's being returned. And if we have a function that needs to return more than one value, we'll be a little more explicit about it and let people know that this function destroys the variables that it's given. Then finally we can report what the string concatenation is. Now, when we actually run this thing, we get some interesting results. First of all, we'll compile it here on the first line. We'll talk more about compiling in the next lecture, or one of the ones coming up here. When this program is compiled, we get a warning here. Warning in function main, the getS function is dangerous and should not be used. One of the reasons for that is because it just writes the data that the user types in and puts it wherever you told it to go. And it doesn't check the bounds of that. So if you enter in too many characters, then all of those characters are written into the location pointed at. So when we say getS A, and imagine I type in 2,000 characters, then sure, the first character will be entered in at the first address of the first index of inside the A array. However, all of the rest of the 2,000 characters will be entered contiguously following that first character. So the second 1,000 characters will be written right over the top of whatever else happens to be in memory, and that's definitely insecure, it's dangerous, shouldn't be doing it, but it's great for testing things out here, just to show you what can happen. So when we do it here, we'll run our program, getS stringcat, enter the first string, here's our first string, here enter the second string, here's our second string, and then concatenation of the two is this joint string here. Now substrings in the C language are not something that's built in. So we're not able to see, there isn't just a direct function you can call that's going to get a substring from the middle of a different one. So let's take a look at the program that we have here. First of all, again, standard I/O included at the top. Here's our main function that won't return anything. Define two separate arrays, string and sub. And we'll define a few integers all in a row here, all in the same command, the same line. We have position and length, which are uninitialized, and then C, which we'll set equal to 0. Here we'll give the user a notice that they need to input a string, so let them know what's going on, and then go ahead and get that string and dump it into here. Then we'll printf a separate line, informational text to the user, enter the position of the first character that you want located within that string, then a space, and then the length of the substring that you're interested in. Then we call the scanf function. And what scanf does is it takes, in this case, two separate numbers. It's going to pull the user is going to enter in data, and then it will separate that data out based on where that space is. And the first half, or the first part to the left of the space, it'll put it into this decimal variable, which here is position. And then the right to the right of that space will be positioned the decimal value, which is where the length array is. And note here that this little ampersand is in reference to the address of these particular character arrays. So you put position here, position is our integer and length is our integer. So we're saying we're going to take in the positions that have been entered here and store them into the integers that the user has declared. Then in our while loop here, we're going to start from a C value of 0, and as long as C is less than the length that was entered by the user, then we'll start processing these internal commands. And the while loop goes from this curly brace down to this curly brace. First thing that we'll run is our array sub, which has no data in it so far. Starting at index 0, we're going to set that equal to what is in our larger string that the user entered their data into, starting it at the position that the user told us to start in the scanf there, add on to that from there wherever we currently are, which is what C stands for, -1. And the -1 is just there for the 0 indexing of the array versus what we as humans would say as a position. So first position is actually index 0. Second position in an index is actually position 1 in terms of the index. So we got to be a little careful there, and the -1 helps fix that. After that assignment is done, then we go ahead and increment our iterator here, this C variable that we're using. So this thing will run until the C has exceeded or has become equal to the length of the substring that we were looking for. Then the all-important assignment here of wherever C ends up, it was incremented and then tested and did not run a subsequent entry of this string assignment line, which means that it is currently sitting at a value that has not been assigned. We are going to put a null terminator there, which is required in order for this thing to actually be a string that has an ending point. Lots of chaos happens if you don't do that, and we'll look at that in the upcoming strings lecture. Alright, then we'll print it out that the required substring is, and then here is the string. So the output looks like this. So when we compile this thing, we'll get the typical warning about using getS, and again, it's really bad. There's lots of other ways to do it. I showed you scanf here as an alternative, and then we'll run our substrings program. First, it asks us to input a string, and here is the input string, or what I typed in, test string, and then it asks us to enter the position of the first character, a space, and then the length of the substring. So here is 2, the space, and the lengths of the substring. So these characters here came from what was entered previously, starting at position 2, which is, here's 1, here's 2, the E in test, and that goes through 6 different characters. 1, 2, 3, spaces 4, 5, 6. The last one is the T. So we grabbed all 6 characters as a substring out of that string. So this is just showing us this little bit of character assignment. We're seeing some array, we're seeing fetching data from arrays. We're seeing some C standard I/O functions in scanf and printf. So a lot of different moving parts here. Yeah, alright, let's move on to arrays. So looking at something a little more complicated in terms of arrays, but not too much more compared to what we've done before. The output for this one, let's go through that here first on the right. So we're going to compare this, or we're going to compile this particular program, and then let's run it. And what it does is it says, enter the number of elements in the array. And the number of elements here will be 5. So let's say 5. And then it'll say, okay, enter in 5 different integers. So then I entered in 5 different integers. Then it tells us that the maximum element, the largest element here, is at location 2, which is this one here, and the value is 9. So that's true. So this thing apparently is gathering data, putting it into an array, and then it is going to tell us which one is largest. Let's see how that works. So here's an array, and this one goes up to 100. We have a few variables that we'll be using to track what's happening in terms of the numbers that we're analyzing, and we're saying where we're going to start at. So first we'll go ahead and tell the user to enter the number of elements in an array, and we will stuff that using the scanf function into the size variable, which had no value and now has been given a value. Then we'll tell the user to enter in integers. In this case, it'll be size integers, so we'll output again, this is the number that you told me that you want. Go ahead and now type those in. And now we're going to put the scanf inside a for loop. So what the for loop is going to do is starting at 0, and as long as that C value is going to be less than size, then go ahead and run the following command. And in this case, it's scanf, which we've seen before, which is going to fetch a number and stuff it into the array, and the index that it's going to be stuffed into is our C value, which is incrementing up. So we're using C not only to tell us how many of these integers we're supposed to fetch, but also which position in the array to store them in. Then we will start our search here for the largest element, and we're going to assume, let's just start because we have to start somewhere. Our base case is going to be that the maximum, again maximum is an integer, let's say that our maximum integer is at array position 0. So index 0, the first position, let's just say that's the biggest one, and then we'll move on from there. This particular for loop then increments through all of the array, starting at index 1, which is the second position in the array. And that's done because we've already stored the first one, so we can start testing from then on. So it's a fairly simple if statement. We're going to ask, is what you're currently looking at bigger than the maximum one that we have? If so, then go ahead and store that maximum value and store the location of that value. And then at the end, we will go ahead and print it out because we will have gathered what location and maximum were, and we're able to tell the user. Okay, let's take a look at round 3 here. So Ken Thompson of Unix fame is definitely unrestrained. However, it's still shaped, and we can clearly tell the difference between hair and between head hair and facial hair, and I think that really goes for something. And look, even a bonus Dennis. That guy's amazing. Richard Stallman, on the other hand, has gone just full white. It's hard to tell what he's looking at, what he's doing. Gandalf apparently has gone brown. That was not something I thought he would do. Alright, let's take a look at pointers. Pointers are going to be one of the more complex and challenging aspects in the C programming language. I've tried to break this down to make it be as simple as possible. Let's look at 2 characters that we'll define here at the beginning. First of all, we'll define a character called mychar and another one called mychar2. And note that we haven't given either of them a value. Now let's look at some little graphics over here to help illustrate what's happening. In this box on the left, this is the name of the variable and the address in memory of that variable. And then the contents of that variable are here on the right side. And this little cloud shape lets us know there's no value inside this. Or rather, there is data inside there, but it just happens to be whatever was in memory when this character was allocated. So who knows what's there? You certainly can't trust it. It's certainly not what you want. The addresses of these 2 variables are set by the operating system. It lets us know whatever address is available and assigns it to these variables. In this case, I've made them be, x1111 and x2222 just for ease of looking at which is which. So now let's take our mychar variable, and we're going to assign that a value, which is capital C. So our mychar variable here, now we actually know there's a capital C in it. The address hasn't changed, but our contents of that variable have. Now we're going to define a new pointer. And how do we know it's a pointer? Well, we know it's a pointer because we have a basic data type followed by an asterisk. And that lets us know we're talking about a pointer. And then we have the name of this particular pointer. Now this pointer can only point at a character. That's it. It can't point at anything else. So out here we can illustrate that by showing that the contents of this particular pointer are different than a character. Even though it's a character pointer, the contents are different because a pointer, the contents of a pointer is the address of something else. Pointers contain addresses. That's all they can contain. They don't contain data per se that a human would read. Pointers only contain addresses. This being a variable, this particular pointer gets an address just like anything else. And this particular one happens to have x333333 as its address. To assign content to a pointer, you take the variable and use the equal operator here, and then the ampersand lets us say, I want the address of this particular variable. Now mychar has to be a character in order for it to be storable in my pointer, because my pointer is a char star. So we say ampersand mychar, and that says get the address of this variable, not the contents of it, which we would get simply by saying mychar, but the address of it, which we get by using the ampersand. So here we take the address of mychar, which is 11111, and we stuff it in as the data that my pointer contains. We can output the value of this pointer at any time if we want using printf, and we'll see whatever the address is, but the address doesn't really do us all that much good. Let's define another pointer. This is another char star pointer, and we'll call it mypointer2. We can directly assign this the value of whatever's in my pointer because my pointer is of the same type. And you can always use the equals operator here or the assignment operator when the two variables are of the same type. So that assigns it right over. Here's my pointer 2. It has its own address, which has to be distinct from everything else, but it now contains the same data value as the original my pointer does. Here's my pointer 2. And at this point, we're now going to set my pointer 2 equal to the address of the mychar2 character. So mychar2, its address is 02222, or it's the x2222 address, and we've stuffed that into here. So now our two pointers have two separate addresses. All right, this one's a little more complicated, so stay with me on this. In this case, we're going to overload the asterisk. This is like the third instance of asterisk, or the third meaning of asterisk here. It can be multiplication if you're using it in terms of arithmetic. It can be a designator that says this is not just a char, but a pointer to a char. And in this case, since there's no type in front of it, this means that it is dereferencing, which means de-addressing a particular variable. That means follow the address of whatever my pointer 2 is pointing at and get the actual data value, and let's refer to that instead. So I want to refer to the data storage spot, not the address storage spot. And we're going to assign that equal to whatever is currently held in data of the variable pointed to by the myPointer variable. So let's follow it through pictorially over here. So myPointer2 contains the address 111111, and that particular 2222, because at this point we reassign it. So it contains 222222. That particular address is where mychar2 happens to be. So we are saying let's take the data value of what myPointer2 is pointing at, and in that case that currently has no value. And now we're going to take whatever data is stored behind the myPointer pointer. So myPointer, its data value is x111111, and that particular storage location, or that address, points to this variable, mychar. The asterisk says get the data contents of that variable, and we know that the data contents of that variable are a capital C. So mychar2 is now updated with C. So we have dereferenced in two different ways here. We've dereferenced the holding location for where we're going to stuff this value, and we've dereferenced the pointer that happens to be pointing at another variable. So it's almost like two separate meanings of this dereference operator depending on the two separate sides of the assignment operator, but they are the same. Now technically this is an L value over here, and this is an R value for left and right of an assignment, so they do have slightly different meanings, and here we've illustrated them. The upshot is that we have assigned a character into the same place as another character, and the pointers were used to help make that transition possible. So let's take a look at some commands that you can't do with pointers. So first of all, here are some values from our previous slide. We had myPointer at 3s, and this pointer stores the data value of 1s, which is the address of this mychar character over here. We have another one, myPointer2, which happens to be pointing to this char over here. One thing that you can't do is you can't take a character like mychar and assign it the value of a pointer. They don't fit, and graphically here you can see that this pointer, this address, which is what a pointer stores, doesn't fit into the character bucket that mychar has. Mychar can only hold a character. It cannot hold a pointer to a character. And the inverse is also true, so myPointer happens to be a character pointer, and mychar is a character. You can't stuff a character into a bucket that's reserved for a character pointer. There is no way to dereference a character all by itself. We're already down at the lowest level of indirection, say. We can't follow an address through to get anything else for this particular variable. It's already a variable C, so there is no way to dereference it, no matter what you put on the left or the right side. In this particular one here, we have a pointer, which is a character pointer, and here we are doing something a little confusing. We are saying take the address of myPointer2 and take that address and store it into myPointer. Now that's intriguing because myPointer can hold addresses, right? And get the address of myPointer2, well, it sounds like we're taking an address and assigning it to another address. C saves us from ourselves here by correctly saying that myPointer was declared as of type character pointer only. It cannot store a address of a character pointer. So a pointer to a char can't hold the address of a pointer to a char. So you can't go one level off from the address on this side and stuff it into a simpler version on the left. Here's another no-no. Here we have a pointer to an integer, and we'll call it myIntP, and we're setting that equal to or we're assigning that the value that is inside a character pointer, which is not allowed. Even though these are both pointers, just as above, they are of pointers of different type. So the integer pointer is expecting a pointer of, say, a different size. You can't put a character pointer inside an integer pointer. Interestingly, C will actually allow these 4 lines. It lets the program compile. It will give you a dire warning for them, but it will let the program actually run with no problem. This internal one, or this middle one here, for dereferencing just a raw character, it won't let you do that. It will throw an error, but the rest of them simply trigger warnings, meaning you can do this if you want, but it's not how the language was designed. And in a lot of C, that's going to be the case. It's no seat belts, it's no training wheels, it requires your full attention at all times, and the tools may not help you to avoid an accident. All right, let's take a look here. This particular program, we are called OCRAP pointers. When we compile this thing, it is going to tell us that the target is merely copy me. So let's take a look at how it works. One standard that I like to use is that I name my functions with capital letters. I find that helps me know that these are my functions as opposed to ones that are based off the standard IO set. Just a little trick that you can do. So this particular function, it's going to take in 2 pointers to characters. And we'll talk about the contents of what it does here in a moment. So in our main function, we have a target array and we have a source array. Now this is a string that is an array of characters, so it's a string, and it is something that is changeable. It's mutable. We're saying declare the space in that array and let it be changeable. Here we're also defining a string. It is a set of characters, is an array, but it cannot be changed. Again, more on that in the strings lecture coming up. And the value we're going to assign to this particular char star is copy me. Then we'll run our copy string function with target and source. So here's our target array, which is empty, or at least has no defined values in it. And then we're going to pass in our a pointer to our source string here. Remember, the name of any variable is going to be a pointer to it, or at least in this case because it's a char star. And then we'll print out the result of this thing, which in this case is just the value of the string. So somehow we have taken source and copied it into target and then output that, and we see that. So let's talk about how the copy actually works. Alright, so the copy, we've got our target and our source char stars that are being given to this function. Here we do a while loop, and in this case we're going to dereference the pointer that was given to us for the source. That means follow the pointer through to the actual character value. And this is saying that while actual character value. Now if you remember your while loops, a while loop evaluates to true as long as it is non-zero. So this while loop will continue until it reaches a 0 value, which is a null terminator. And the null terminator is added by default to this source string down here when it's defined. You can't see it there, but it's added automatically when you define a string like this. So this particular while loop is going to run until it hits 0, which is the integer value of a null terminator character. Remember that every character has a corresponding integer value also. It's that ASCII table that translates between the printable character and its integer value, 0 through 256. Alright, so then what it does is similar to the assignment we saw before. We're saying dereference down to get the actual character data and stuff that into dereference down the pointer and put it into the actual storage location. So follow the addresses in both places and just do a character-to-character copy. Then increment both particular arrays. And this is a little nuts. We are saying take the original variable that we were given and add 1 to it. And that works because characters are defined in a space where it's 1 byte per character. So when we add 1 to it by incrementing the pointer source, we're now pointing at the second index in that array of the string that was given to it. And we do that for both, such that when we then go back through the loop and dereference both again, now we're saying copy in the second character into the second bucket in our storage array. Pretty nuts, but it does work. And then finally, like you saw before, we are adding a null terminator to the whole thing at the end. And in terms of Unix beards, the winner is going to be Ed Gold. Ed Gold was a pioneer. He was a very helpful fellow in the BSD movement, which is one of the clones of Unix. And his beard's amazing. Clearly we can see, this is black and white, but we can see he had some tie-dye going on here. He had all kinds of different colors going on between his beard. You can tell the difference between his hair and his beard. And he just didn't care. And he was a great guy. Ed Gold's terrific. And that will do it for our lecture for today. See you next time.